Word. Verizon got this thing with the app. You could just be like, you see what they're doing, Yeah, yeah. See, right? Well, yeah. All right, let me see. All right, let me see what you got.
This one, this is a ratio prop thing is saying,
Mm-hmm.
but it doesn't give me like an option for ratio, so I don't know which way.
All right, I'm just picking up where we left off last week, right? And then we'll do another example. Mhm. So this is a part of your homework. I didn't get to show you guys this yet, right? This is called coefficient of variation. All right. Real simple formula. It's on your formula sheet, so you don't have to memorize it. All right. So here we go. Coefficient of variation. So a disadvantage of the standard deviation as a comparative measure of variation is that it depends on the units of measurement. This means that it is difficult to use a standard deviation to compare measurements from different populations. For this reason, statisticians have defined the coefficient of variation, which expresses the standard deviation as a percentage of the sample or the population mean. So if X bar, right, which is the sample mean, right, and S, which is our sample standard deviation, represent the sample mean and sample standard deviation respectively, then the sample coefficient of variation, written as CV, is going to be the sample standard deviation divided by the sample mean times 100%, right? If mu and sigma represent the population mean and the population standard deviation, respectively, then the population coefficient of variation, CV, is defined to be sigma divided by mu times 100%, right? Notice that the numerator and the denominator in the definition of the coefficient of variation have the same units. So the coefficient of variation itself has no unit of measurement, right? This gives us the advantage of being able to directly compare the variability of two different populations using the coefficient of variation, right? Okay, let's say, for example, I'm running some type of experiment, right? Like, let's say I want to know what does the Bronx think about this guy running for mayor, Mondani or whatever, right? Now, it's impossible for me to ask everybody in the Bronx. So maybe I come to Bronx Community College and I ask everybody, and then I go to Fordham University and I ask everybody, right? But I want to know whose data is more varied, right? Has more spread between it, right? So I would use a coefficient of variation to tell me that, right? The not the population, yeah, the populations of Bronx and Fordham, right? They're different, right? It's like they're different samples. So how do I compare them? I use this to compare them, right? So that's that. Let's look at an example. No. This is after you find the coefficient of variation. This is if you, it's a very particular question when you have different populations and you want to compare them, you know, apples to oranges, you want to compare them, you know. This is something that you can use to compare. All right. Let's look at an example real quick. So coefficient of variation, right? So the Trading Post on Grand Mesa is a small family-run store in a remote part of Colorado. The Grand Mesa region contains many good fishing lakes. So the Trading Post sells spinners, a type of fishing lure. The store has a limited selection of spinners. In fact, the Trading Post only has 8 different types of spinners for sale. The prices in dollars are here, right? Since the Trading Post has only 8 different kinds of spinners for sale, we consider the 8 prices, whatever, data values to be the population. All right. Not bad, right? So we can use a calculator and do it by hand or do it by hand, whatever, to find our mean and our standard deviation, right? So, boop, boop, boop. Since you want to see me do a standard deviation, let's do one right now. All right. Real quick, let's just review the mean. Remember, the mean is what? The sum of x divided by n, right? So you're going to add all these numbers together, 2.10, 1.95, 2.60. You get the idea, right? All the way up to 2.25. And then you're going to divide by how many numbers you have there. So we have what? 1, 2, 3, 4, 5, 6, 7, 8. What's my mean? And then divide by 8. So what's the mean that we got here? You want me to do it? I thought y'all was going to do it for me. All right, I'll do it. Hold on. That's why I gotta do my lesson like this because
437 something.
all of that.
You said divided by 8, right?
Yeah.
Yeah, it's the total order added up to 17.15 divided by 8. For the purpose of 2.1, 4 3 something. Yeah.
Let's see if y'all are right. 2.14375. Okay. So that's my mean. All right. Just wanted to recap that. Now, I'm gonna show y'all a different way to do the standard deviation, an easier way. All right. So we have another formula called the computation formula. I didn't have a chance to show you that yesterday, but I did show you the formula yesterday. This is how you do it. So first thing you want to do is you have to write down all your x values. The x values are the numbers that was given to you right here. So 2.1, 1.95, 2.6. I'm literally just copying the list. That's all. I'm not changing nothing. 2, 1.85, 2.25, 2.15, and then 2.25, right? After that, what do you want to do? You want to add up, you want to sum x, you want to add up all of these numbers, right? So when I add up all these numbers, what do I get? Not the mean. Let me see. I'm feeling lazy. 17.5. All right. 17.5. 15. Whoops. 17.15. So again, I got that simply by just adding all these numbers up, right? Decimals and all, right? Next, over here, you want to square each number, each one, right? So let me square these numbers real quick.
And the way you do it in the calculator is with the parentheses, right? In the square.
Yes, each number.
And you said that's 17.15
From adding all the numbers, 2.1 plus 1.95 plus 2.6, etc. Right?
4.
441, very good. All right. So for the first one, which is again 2.1 squared, I got 4.41. Next one, I got 3.8025. Next one was 6.76. 4 flat, 3.4225, 5.0625, 4.6225, and then 5.0625.
So it should only be four numbers after the decimal.
I like 4. I like 4. Yeah. So again, you're just squaring them individually, right? And you should get these numbers here. After you square all these numbers, you want to add them up to get their sum, right? So down here, this is called the sum of x squared, right? Let's take a look at that.
37.
You got 37? It probably is. Let me see. 37, right? So I got 37.1425, right? Now that you got that sum, we're going to plug it into the formula, right? So our variance formula, s squared, by the way, is going to be the sum of x squared minus, open parentheses, the sum of x, and then you're going to square that answer divided by n, and then all of that divided by n minus 1. This is on your formula sheet, by the way, right? All you have to do is just plug in the numbers that you have right there, right? So this is going to be 37.1425 minus, open parentheses, the 17.15 squared divided by how many numbers did we have? 8, right? And then on the bottom now, we have 7, right? Which is 8 minus 1, right? And then after that, little calculator, pop, 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 and then that's it. It's still wrong. But wait, keep in mind though, this is not the standard deviation, this is the variance. Yeah, this is the variance. So let me get the variance real quick so we can verify this. Yeah, this first one is the variance. And yes, I'm like hella cheating if you're wondering. Right? So when you do it in the calculator, you should get 0.053884. That's the variance. And then to get your standard deviation, S, remember that it's always the square root of your variance. So you're going to square root that number that you just found, the 0.053884, and then that's going to be your standard deviation. Mhm. Yeah. So now let's see what I get. So now I have 0.232129. This is my standard deviation. And that's it. Questions on this? We're good? Well, this is a different formula. This is a different formula. Mm-hmm. Yeah. All right, let's go ahead. Yeah. Yeah. And your calculator. So let's continue with the lesson. There's a little bit more to it, right? After we find the mean and the standard deviation, we want to do the new thing that we just learned, which is the coefficient of variation. So, written in English, we use the calculator to find the 2.14 and the 0.22, right? Even though our numbers are a little bit extended, right? Our numbers are a little extended, right? You can round it off, because we're talking about money, right? Depends on the story of what you're working with. Money has two decimal places, so that's why we get away with rounding this off to like 2.14, for example, or 0.22, right? Anyway, since the computation formulas for the mean and x bar and mu are identical, most calculators provide the value of x bar only. Use the output of this key for mu. The computation formula for the sample standard deviation S and the population standard deviation S are slightly different. Be sure that you use the key for the standard deviation, sometimes designated as sigma n or sigma x. Now, let's talk about the new thing that we want to talk about, computing the coefficient of variation of the prices of the trading posts and comment on the meaning of the results. So our coefficient of variation, CV, right, is going to be our standard deviation that we just found, that's 0.22, divided by our mean that we found, which was a 2.14 times 100. So this would be my coefficient of variation, 10.28%. Please remember the percent. That's the reason why we multiply it times 100, because it's a percent. All right. So, right. Mm-hmm. So, let's talk about what this actually means. All right. So the coefficient of variation can be thought of as a measure of the spread of the data relative to the average of the data. So since the trading post is very small, it carries a small selection of spinners that are priced similarly. So the coefficient of variation tells us that the standard deviation of the spinner price is only 10.28% of the mean. All right? So that's what it means. All right. Last topic. So we're going to talk about something called Chebyshev's theorem. Believe that's on your homework too. Right? Yeah. So Chebyshev's theorem. So from our earlier discussion about standard deviation, we recall that the spread or dispersion of the set of data about the mean will be small if the standard deviation is small, and it will be large if the standard deviation is large. If we are dealing with a symmetric bell-shaped distribution, then we can make very definite statements about the proportion of the data that must lie within a certain number of standard deviations on either side of the mean, right? And then this will be discussed later in chapter 7, blah, blah, right? So Chebyshev's theorem, here we go, right? For any set of data, either the population or the sample, and for any constant k greater than 1, the proportion of the data must lie within k standard deviations of either side of the mean and is at least 1 minus 1 over k squared. So this should say equals to a percentage, right? Put another way, for sample data with mean x bar and standard deviation s, at least 1 minus 1 over k squared fractional part of the data must fall between x bar minus ks and x bar plus ks, right? That's it. So, give you a little bit more information about that. This is Chebyshev's theorem. I could say it, I just don't know how to spell it. That's what it is. Don't know how to spell it. All right. So here are the results for Chebyshev's theorem. For any set of data, at least 75% of the data falls between mu minus 2 sigma and mu plus 2 sigma, right? So that's two standard deviations to the left and two standard deviations to the right. At least 88.9% of data falls in the interval between mu minus 3 sigma and mu plus 3 sigma. and at least 93.8% of the data fall in the interval between mu minus 4 sigma and mu plus 4 sigma. So the result of Chebyshev's theorem can be derived by using the theorem and a little arithmetic. For instance, we can create an interval k equals 2, standard deviations on either side of the mean. Chebyshev's theorem tells us that 1 minus 1 over 2 squared is equal to 1 minus 1 over 4, which is equal to 3 over 4, or 75%. Right? So that's how we do that. You just plug in the value and it gives you the percent of the data that is being captured in your sample or whatever. All right. Little commercial break. So is the minimum percentage of data in the mu minus 2 sigma to mu plus 2 sigma interval? Notice that Chebyshev's theorem refers to the minimum percentage of data that must fall within the specified number of standard deviations of the mean. If the distribution is mound-shaped, an even greater percentage of data will fall into the specified intervals, right? Which we'll see in the empirical rule. So more specifically, right? What does Chebyshev's theorem tell us? Chebyshev's theorem applies to any distribution. It tells us the minimum percentage of data that fall between the mean and any specified number of standard deviations on either side of the mean. A minimum of 88.9% of the data fall between the 3 standard deviations below the mean and the 3 standard deviations above the mean. This implies that the maximum of 11.1% of data fall beyond 3 standard deviations of the mean. Such values might be suspect outliers, particularly for the mound-shaped symmetric distribution. All right. Good stuff, good stuff. Let's go through a quick example and then we'll move on. Well, actually, we'll call it a day at that. Quick example. After this, y'all should be able to finish y'all homework. All right, so Chebyshev's theorem. So Students Who Care is a student volunteer program in which college students donate work time to various community projects such as planting trees. Professor Gill is the faculty sponsor of the student volunteer program. For several years, Dr. Gill has kept a careful record of X equals total number of work hours volunteered by a student in the program each semester. For a random sample of students in the program, the mean number of hours was X bars equal to 29.1 hours each semester, with a standard deviation of S is equal to 1.7 hours each semester. Find an interval from A to B for the number of hours volunteered into which at least 75% of the data of this program would fit in. So very simply, going back up here, we know that 75% of our data falls in between 2 standard deviations to the left and to the right. So that's it for the question. You just kind of plug it in and that's the end of it, right? So according to the result of Chebyshev's theorem, at least 75% of the data must fall within 2 standard deviations of the mean. Because the mean is X bar equals 29.1 and the standard deviation is equal to 1.7, just plug in those numbers. 29.1 minus 2 times 1.7 to 29.1 plus 2 times 1.7. Boom, boom. And we have our interval. That's the whole Chebyshev's theorem right there. That's all it is. So they're gonna give you some percentage and be like, all right, in between, how many standard deviations is it? And you're just gonna tell them, right? The lower bound to the upper bound. All right. So at least 75% of the students would fit into the group that volunteered from 25.7 to 32.5. All right. Last but not least, all right, it's a special note for after you get out of statistics. All right. Averages, such as the mean, are often referred to in the media. However, an average by itself does not tell much about the way the data are distributed about the mean. Knowledge about the standard deviation or variance along with the mean gives a much better picture of the data distribution. Chebyshev's theorem tells us that no matter what the data distribution looks like, at least 75% of the data will fall within two standard deviations of the mean, right? As we will see in a later chapter, when the distribution is mound-shaped and symmetrical, about 95% of the data are within two standard deviations of the mean. Data values beyond two standard deviations of the mean are less common than those closer to the mean. In fact, one indicator that a data value might be an outlier is that it is more than 2.5 standard deviations from the mean. All right, that's it. So any questions? That's it. Copy and paste the formula. That's it. Anybody want to go over any web work questions? We got like a good 10 minutes left if y'all want. 4? Yeah, give me one. Yeah. Yeah. Awesome, you got it right. Awesome, good job.
Can I turn this into like a decimal?
Not a decimal, right? What you want to do? I'm sorry. So here's what you want to do, right? You got 1/2 and then square root 45, right?
Mhm.
What's the largest perfect square that goes to square root 45?
Thursday, 5 drink on. Oh.
5 times what?
4 day week. Nine.
9, right? So this becomes 1/2, right? And we're breaking this down. Square root 9 times square root 5. And what's the square root of 9?
Doesn't look like. I don't know.
Right? It's 3, right? So this is 1/2
You know, I was gonna
times
stop, then I was like, I don't know, cause I know when I see 9, I see like 3.
3 times 3, right?
Yeah.
That's the reason why it's 3. That's the exact reason why it's 3. After that, we just multiply these straight across, right? So this becomes 3 square root 5 over 2. That's it. Your question is asking for, oh, they want the fraction on the outside. So 3 over 2 square root 5, like that. And they just fill in A, B, C, and that's it. Tomorrow, yeah. Tomorrow, new lesson. The new lesson is not on the test. So y'all know.
But it's open?
I think so tonight. Yeah.
I'm gonna email you again for the link.
I got you. Yes, yes, please. Yes. That's fine. It's fine. And I'll just watch the recording and then do the homework. It's fine. But the homework for tomorrow is not on the test next week, Thursday. All right? Hey, did you have a chance to visit them yet?
No, not yet.
Okay, so just let them know, like, you have a test coming up, it's gonna be Thursday next week, right? And then, what's gonna happen is they have to send me an email, and I can email it back to them, and you can take it when you have time. Yeah. And that's it. Well, it should be good.
Yeah. Anything right now that has helped me a lot in during homework is,
Awesome, I like that.
yeah, I have it on the phone.
Good. But we need a real one for the test.
I know, I have one, I just don't have the charger for it.
They have it here on campus. You can charge it on campus. Yeah. Also, that same office I'm sending you, they have the charger. If you want to charge it over there, you can hang out and charge it over there.
But also I feel like I need to buy one, cause I already own one, so I need to buy the other.
I got you. I got you.
Yeah.
All right. Sounds good. Oh, your other classes going good? No, let me stop this real quick.
Me? No, I'm going home.
No, hold on.